In data mining and knowledge discovery, a fundamental problem is to analyze causes and effects among random variables and random events. Causal discovery is a technique that can extract causal relationships between variables and encode the relationships into causal graphs. This technique is useful in many fields, such as biomedical science. However, the low efficiency for causal discovery tools limits its applications. This presentation introduces a novel FPGA accelerated approach for causal discovery. Assume that we have a matrix containing sample data from 5 variables. A causal discovery algorithm can find the causal relationships between the variables and turn the relationships into a graph with 5 nodes. Each node represents a random variable, while an edge from node A to node B means that variable A is a cause of variable B. Causal discovery is computationally expensive. A causal discovery task with less than 2,000 variables can still take more than 3 days to run on multi-core CPUs. There are a few different types of causal discovery methods. This study focuses on one of them, namely constraint-based causal discovery. The core calculation of constraint-based causal discovery methods is the conditional independence test, or the CI test. In particular, a CI test can be considered as a Boolean function with 3 arguments. This function tells us whether 2 random variables A and B are conditionally independent, given a set of other variables C. The set of variables C provides the common information for the conditional probabilities during CI tests. Therefore, the random variable set C is also called the conditioning set of the CI test. In constraint-based causal discovery methods, CI tests often dominate the execution time. In this study, we propose an FPGA accelerated approach for constraint-based causal discovery. The acceleration of constraint-based causal discovery is a considerable challenge for FPGAs. In particular, the execution of conditional independence tests appears intractable for FPGA-based acceleration. The main contribution of this paper includes the following: an acceleration strategy that shifts the speed bottleneck from CI test execution to a novel FPGA-friendly CI test generation process, an FPGA accelerated causal discovery design and its implementation based on the proposed strategy, an empirical study comparing the proposed approach against state-of-the-art accelerated causal discovery tools on CPUs and GPUs regarding speed and accuracy. Our accelerated implementation running on Intel Arria 10 GX FPGA shows a superior accuracy-speed trade-off in 12 causal discovery problems. The experimental implementation achieves up to 8.8 times speedup over the cuPC software running on an NVIDIA GeForce RTX 2080 Ti GPU. It also achieves up to 155 times speedup over the stable.fast software running on an Intel Xeon Silver CPU. A typical causal discovery workflow can be roughly divided into 3 main calculations: initialization, CI tests, and post-processing. The generation and execution procedures for CI tests is usually the speed bottleneck. We find that the generation and execution procedures for CI tests are tightly coupled in typical causal discovery algorithms. As a result, the generation and execution procedures should take place on the same hardware platform to minimize latency. To facilitate acceleration, we hope to run the 2 procedures on different hardware platforms. To decouple the generation procedure and the execution procedure of CI tests, we propose an algorithmic framework shown in this slide. In this algorithmic framework, the generate CI tests function is a CI test generation procedure. Our algorithmic adaptation allows the generation and execution procedures to take place on two separate hardware platforms. Since the execution procedure of CI tests takes most of the causal discovery time, a straightforward way to accelerate it is to perform CI test execution on the FPGA platform and leave the generation procedure on the CPU platform. However, we found it very difficult to accelerate CI tests on FPGAs. The numeric operations in CI tests usually lack efficient FPGA implementations. The problem is significant even for simple CI test algorithms. As a result, we propose to address the speed bottleneck without accelerating CI test execution. Our key insight is to shift the speed bottleneck from CI test execution to CI test generation. Instead of making the CI test execution faster using FPGAs, we create an FPGA-friendly CI test generation procedure that reduces the number of CI tests so that the execution of CI tests no longer dominates the causal discovery time. In particular, we propose an algorithm, conditioning set filtering, or CSF, that generates fewer CI tests than conventional methods. The CSF algorithm evaluates a score for each conditioning set. The conditioning sets with low scores are filtered out so that they can no longer attend any CI tests. In other words, the CSF method shifts the bottleneck from CI test execution to CI test generation. The newly introduced calculation in CI test generation is still computationally expensive, but it can be accelerated on FPGAs. On the other hand, the execution of the reduced set of CI tests can finish within a reasonable time on CPUs. We accelerate the CSF procedure using FPGAs with a 4-step workflow. First, the CPU generates a short list of conditioning sets. Second, the FPGA computes the score for each conditioning set in the short list and returns a list of scores. Third, the CPU obtains the score from the FPGA and computes a threshold. Fourth, the CPU takes a list of conditioning sets with higher scores than the threshold. At this stage, the CPU can work out a set of CI tests based on the high-score conditioning sets. The FPGA design accelerates the evaluation of the score function. In particular, the FPGA design includes a queue to buffer the conditioning sets received from the CPU. At the beginning of a score evaluation process, the queue releases a conditioning set. The conditioning set data buffer fetches the data vectors for the conditioning set. Next, the subscore evaluation modules evaluate the subscores in parallel. Meanwhile, the accumulator sums up the subscores. When the accumulator finishes accumulating all the subscores for the conditioning set, it sends the final score back to the CPU. We run a recursive method to solve the least squares problems in score function evaluation. An optimization applied to the least squares solver is the use of the delayed sample mean. This optimization avoids resource usage for residual storage and central moment evaluation. Another optimization for the least squares solver is on the exit condition. The conventional exit conditions are based on the weight vector. However, we set the exit condition based on the curtices. This setting can potentially cut down the number of iterations for the least squares solver. In addition to the optimizations on the least squares solver, we run additional edge removal on the host CPU when FPGA is busy. Specifically, once the FPGA starts to calculate the scores for the shortlist, the CPU starts to execute CI tests to remove edges using conditioning sets whose scores are slightly below the threshold in the previous shortlist. This optimization can use idle CPU time to speed up convergence. The proposed CSF-based approach has 3 FPGA-friendly properties. First, the CPU FPGA communication time is small compared to the evaluation time of the score functions. Second, CSF allows efficient exploitation of on-chip memory resources on FPGAs. The least square solver can spare a lot of on-chip resources to store data. Practically, we should use the on-chip memory to store the entire dataset to maximize computational efficiency. Third, the evaluation of the score involves a large number of low-dimensional least square problems. Efficient solutions to these problems require the exploitation of fine-grained parallelism. In contrast, CSF may not benefit other processors, including CPUs and GPUs, for 2 reasons. One reason is that an efficient design requires a fine-grained load balancing mechanism for function evaluation, which may lead to expensive thread management costs for CPUs and GPUs. The other reason is that CPUs and GPUs may not be efficient for low-dimensional least square problems in CSF. Unlike FPGAs, hardware facilities on CPUs and GPUs that support least square solvers cannot be customized to fit low-dimensional vectors. On the contrary, these facilities on mainstream CPUs and GPUs are usually optimized for high-dimensional vectors to improve computational efficiency for applications such as deep learning and numerical simulation. We conduct an empirical evaluation of the proposed approach using the experimental implementation in the discovery of undirected and directed causal graphs. 4 state-of-the-art causal discovery tools running on CPUs and GPUs are compared in our evaluation. We compare these tools since they involve concerns and optimization for speed. The benchmark graphs in the experiments include all the 9 benchmarks classified as large or massive graphs in the BNLearn Causal Discovery Data Repository. Since there are rarely large causal discovery problems with ground truth, we include 3 synthesized graphs to investigate the capability of different causal discovery methods on large causal graphs. The FPGA platform is based on Intel Arria 10 GX FPGA, which has 20nm technology. We compile and run the design at 240 MHz on the FPGA. The CPU platform has an Intel Xeon Silver 4110 CPU. The CPU comes with 14nm technology. It has 8 physical cores supporting 16 threads. The base frequency is 2.1 GHz, while the maximum turbo frequency is 3 GHz. The GPU platform is based on an NVIDIA GeForce RTX 2080 Ti GPU, which has 12nm technology. It has 4,352 CUDA cores running at around 1.5 GHz. For each dataset, we plot the accuracy and speed for each implementation on a 2D space. An implementation appears in the plot even only if it finishes execution in 2 hours. The speed measure is the total execution time in seconds. Low yield time means faster execution. The accuracy measure is the structural homing distance. A low yield structural homing distance means higher discovery accuracy. As a result, a good trade-off corresponds to a point near the bottom left corner. The primary conclusion from the results is that the proposed FPGA accelerated implementation achieves a superior trade-off between accuracy and speed. In particular, given the same execution time, the proposed CSF-based approach is likely to offer the highest accuracy. Given the same accuracy requirement, the proposed approach is likely to finish in the shortest time. The accuracy of CSF is high. Specifically, CSF achieves the best accuracy in 10 out of 12 datasets in undirected graph discovery, and 11 out of 12 datasets in directed graph discovery. The key factor behind the high accuracy is as follows. The number of CI tests provided by the FPGA accelerated generator is small. The small quantity of CI tests allows complex but accurate CI tests to finish within a reasonable time on CPUs. In contrast, to pursue high speed, the other 4 tools only support simple but inaccurate CI tests. The speed of CSF is also outstanding, especially for high-dimensional datasets. In both discovery tasks, CSF achieves the highest speed in 7 out of 12 datasets. In particular, CSF is the only approach that finishes within 2 hours for the Pathfinder dataset. When CSF does not demonstrate an advantage on speed for a dataset, there is little need for acceleration for this dataset, since software tools are sufficiently fast. We also aim to provide a direct speed comparison between our CSF-based experimental implementation and other causal discovery tools. However, the experiments on the accuracy-speed trade-off do not support a direct speed comparison because different tools end up with different accuracy. Fortunately, we can terminate our experimental CSF implementation early to obtain a shorter execution time and a less accurate causal graph. For each causal discovery problem, we measure the execution time and accuracy of the reference method. Then, we run the proposed implementation and take the execution time when it reaches the same accuracy with the reference implementation. In all the tests, our proposed FPGA implementation can reach the accuracy of cuPC and stable.fast software within 30 seconds. The best speedup against GPUs and CPUs are respectively 8.8 times and 155.7 times. To sum up, causal discovery is a critical but computationally demanding procedure in data mining and knowledge discovery. A common speed bottleneck for constraint-based causal discovery is the execution of CI tests. Conventional acceleration strategies speed up the execution of CI tests by running them in parallel. However, it is difficult to accelerate this calculation using FPGAs. Our key insight is to shift the speed bottleneck from CI test execution to another calculation to facilitate FPGA acceleration. Instead of accelerating the execution of CI tests using FPGAs, we propose an acceleration strategy that shifts the speed bottleneck from FPGA-unfriendly execution procedure of CI tests to FPGA-friendly generation procedure of CI tests. The proposed approach allows the execution of CI tests to finish within a reasonable time on CPUs. On the other hand, we develop an FPGA-accelerated design to remove the new speed bottleneck, CI test generation. Compared with state-of-the-art causal discovery tools on CPUs and GPUs, our experimental implementation on an Intel Arria FPGA shows a superior trade-off between accuracy and speed in 12 causal discovery problems. Thank you.